In this segment, we will consider an important property of functions known as continuity. In previous segments, we discussed that limit of a function at a point and value of a function at a point are different concepts. For example, function may have limit defined at a point, but it does not have value defined at that point. Or the other way around, maybe value of the function is defined, but limit does not exist at that point. And if we look at the graphs of such functions, we will notice that these graphs will have holes or maybe some places where the curves do not meet from left and right. On the other hand, there are functions for which limit at a point and value at a point coincide, meaning that both limit exists and value at a point is defined, and that is the same value. If we look at graphs of these functions, we notice that they are given by curves that are continuous without skips or disruptions. We will say that these functions are continuous. The concept of limit is instrumental for defining continuous functions. It turns out that working with continuous functions is easier than with the other discontinuous functions. In particular, models that are described by continuous functions are easier to analyze and to compute. We're therefore looking for ways to distinguish continuous functions from the other not continuous or discontinuous functions, and we are interested in tools to classify functions, determine where the functions are continuous, where the functions are not continuous, and all the related facts about continuous functions. So let us start from looking at the definition of a continuous function. We say that a function f is continuous at a point a if limit of function f as x approaches a is equal to the value of function f at point a. This definition implies three facts that can be checked independently. First, we need to make sure that function is defined at a point. Second, we need to make sure that limit of the function exists at that point. And third, we need to make sure the value of the limit at the point is equal to the value of the function at the point. If the function fails one of the three conditions, then we say that function is not continuous at that point, and we call such functions discontinuous. Let us try to apply definition of continuous function to the following examples. We have three functions given on the plots, function f, function g, and function h over here. We will look at the graphs of these functions and we will determine where these functions are continuous and where these functions are not continuous. The three conditions that a continuous function must satisfy are listed over here. So we can see that at most points, both f of x, g of x, and h of x are continuous. The limit will exist, the value of the function will be defined, and limit will coincide with the value of the function. Now, if we are looking for places where these conditions fail, we would be looking at the places where the function is undefined, or where the limit does not exist, or where the limit exists but not equal to the value of the function. We can definitely see such places on the graph of function f of x, given here in purple. So if we look at function f of x, we notice that limit of function f of x as x approaches 2 doesn't exist. Therefore, condition 2 is violated. So we conclude that function f of x is discontinuous, which means not continuous, at x equals 2. Now let us take a look at function g of x. We notice that at point -1, limit of function g of x is equal to 4 as x approaches -1. And that's good. That means the second condition is satisfied. We can check that off. Here we go. Second condition is satisfied. But then we check the first condition. Is the function defined? As a matter of fact, the function g is defined at -1, and the value is equal to 2. So the condition 1 is also satisfied. However, when we look at the condition 3, we notice that limit of the function g as x is approaching -1 is not equal to the value of the function g at point -1. Therefore, condition 3 is violated. So we conclude that the function g of x is not continuous at x equals -1. Our last example is function h of x, and we notice that h of x is continuous everywhere except one place. If we zoom in, we'll see this rapid oscillations as x is approaching -1 according to this scale. This point is -1, and as we approach -1, we see rapid oscillations in the function. As a matter of fact, this function is discontinuous. And the reason it is discontinuous is that the property 2 is violated. The limit as x approaches -1 of h of x does not exist. Let us now try to apply definition of continuity to functions that are given by formulas. So our first function is g of x given by the formula x cubed minus 27. And the question is this function continuous at 2? Well, as a matter of fact, this function is continuous at 3, and here's the check. Well, first of all, how do we compute g of 3? We can substitute 3 instead of x, and we have 3 cubed minus 27 equals 0. Now, let us look at the limit of function g of x as x is approaching 3. Well, g of x is a polynomial, and we can evaluate limit of polynomial by either using the substitution theorem or maybe just applying limit laws. In particular, to evaluate limit of g of x, we can write that it's going to be limit of x as x is approaching 3 cubed minus 27. The limit inside parentheses is equal to 3, so we have 3 cubed minus 27 equals 0. We notice that limit of the function g of x as x approaches 3 is equal to 0, which is the same as the value of the function at value 3. So we conclude that g of x is continuous at x equals 2. Now, this statement shouldn't come to us as a surprise. For polynomials, we had the substitution theorem, and it says that if we need to evaluate limit of a polynomial p of x as x approaches a, we evaluate it by a substitution. Now we have a different way to restate it. This pretty much says that polynomials are continuous functions. We will talk about it a little bit later. Let me modify the previous example a little bit, and I add a denominator. In numerator, I will have x cubed minus 27, and in the denominator, I have x minus 3. The question is this new function continuous at x equals 3, or is it discontinuous? And this function turns out to be not continuous at x equals 3 because the very first condition is violated. The first condition is that the function should be defined at the point. And we notice that this function is undefined when x equals 3. Because the first condition of continuity is violated, the function is not continuous. Let us modify the example just a little bit more, and now we're talking about a piecewise defined function. when x is not equal to 3, we will use the expression above. But when x is equal to 3, we say that the function is equal to value 23. The question is this new function continuous at x equals 3? Well, to check the continuity, we need to check three conditions. First condition, f of a is defined. Second condition, limit of the function f of x as x approaches a exists. And the third condition is that limit and the value are the same. We notice that for this new function, value of 3 is defined and is equal to 23. So that condition checks out. Next, let us consider limit as x is approaching 3 of f of x. When we talk about limits of functions, in particular limit at point x equals 3, we do not need to consider value of the function at the point itself. So that second part of the definition becomes not important for the sake of the limit question. Instead, we're going to use the portion that is working for all points but x equals 3, which is the top portion. And we will substitute that top portion for the function in the limit. To evaluate this limit, we need to produce some manipulations with the fraction. In particular, let me copy that limit as x approaches 3. And then in the numerator, we will factor x cubed minus 27 as x minus 3 multiplied by x squared plus 3x plus 9. One can verify that if you multiply that through and cancel everything that cancels, we will have x cubed minus 27 back. In the denominator, we have x minus 3. We notice that x minus 3 and in the numerator and x minus 3 in the denominator cancel, resulting into 1. X squared will approach 3 squared. 3x will approach 3 times 3, and 9 will stay the same. Overall, we'll have the following. So the denominator cancels, and all that's left is 3 squared plus 3 times 3 plus 9, which is 9 plus 9 plus 9, which is equal to 27. So limit of the function f of x as x approaches 3 is equal to 27. So far, we were able to check off property 1 and 2. Now we need to go to the property 3. And what we see is that limit of the function f of x is equal to 27. However, value of the function at 3 is equal to 23. And these two values are not the same. Therefore, the condition 3 is not satisfied and the function is not continuous. Now, let us consider a slightly more elaborate example. I have a function given using a piecewise formula, and for x not equal to 0, the function can be evaluated using this expression, x multiplied by sine of 1 over x. The graph of that expression, x multiplied by sine of 1 over x, is given here in green. So it's going to be a function that is oscillatory and it gets more and more oscillations as x is approaching 0. Exactly at 0, that expression is undefined. Instead, we will use the second expression to evaluate function at 0. We will set that function to be equal to 0. The question we are asking, is the function continuous at x equals 0? To answer the question, we need to check the three conditions. Is the function defined? Does the limit exist? And is the limit the same as the value of the function? Let's start with the condition 1. What is the value of function at point 0? According to this definition, that value is perfectly defined as equal to 0. So the condition 1 checks out. The second condition is to consider limit. As x is approaching 0, of the function f of x. Now, that limit is slightly harder to verify because we cannot evaluate that limit by substitution. In fact, in the previous segment, we were talking about the squeeze theorem, and we were evaluating that very same limit using the squeeze theorem. Let me just copy that result from the previous segment. We noticed that x sine 1 over x was bounded by absolute value x on one side and negative absolute value x on the other side. Now it's less than or equal to. Just to verify, so the absolute value x, you can think of it as these two lines. That would be y equals absolute value x. And y equals negative absolute value x can be thought as these two lines. And according to this picture, their absolute value of x and negative absolute value x are bounding the function. As x is approaching to 0, we observe that limit of negative absolute value x is 0. Limit of the positive absolute value x is also 0. So by the squeeze theorem, limit of x sine 1 over x as x approaches 0 exists and is equal to 0. That's the same limit as for the right and left functions. Very good. So what we just established, that this limit exists and the property 2 checks out. Now, the third property is to compare whether the limit has the same value as the function. And in fact, they do. Limit of the function and the value of the function at 0 are the same. Therefore, we conclude that f of x is in fact continuous at x equals 0. Let us introduce some additional definitions that are useful to work with functions. In many cases, it is convenient to generalize the definition of continuity to include something that we call one-sided continuity. So here's the definition. We will say that the function is continuous at a point from the right if limit of the function exists from the right at that point and is equal to the value of the function at that point. In a similar fashion, we'll say that the function is continuous at a point from the left if limit of that function exists as x approaches point from the left and the limit is equal to the value of the point. The graph on the right provides an illustration. So in particular, the f of x in this example is not continuous at either x equals -2 or x equals -1. And the reason for that is that the second property is broken. Limit of this function as x approaches -2 does not exist. And also the limit does not exist as x approaches -1. However, the one-sided continuity holds for that function. In particular, if we look at the limit of the function f of x as x is approaching -2 from the left, we'll notice that that's the -2, and we would be approaching value from the left. And we would see that the limit from the left is approaching value of the function at -2. Because of that, we will conclude that f of x is continuous at -2 from the left. However, the function is not continuous at -2 from the right. In a similar fashion, if we look at the limit as x is approaching -1 from the right of the function f of x, which is over here, that's -1, And as we approach it from the right, we see that the value of the function is approaching value of the function at -2. Therefore, function f of x is continuous at x equals -1 from the right. Now, if we have an interval and we observe that a function is continuous at every point on that interval, we will say that the function is continuous on an interval. For the endpoints, we use one-sided continuity. When the function fails to be continuous, sometimes it's instructive to look into the detail. What type of properties were violated and in which way the function is discontinuous? There is in fact a hierarchy from less severe to more severe violation of continuity, and we will talk about that next. The least severe violation of continuity is known as a removable discontinuity case. In this case, a function can be made continuous by modifying it just at one point. You can also generalize it to modifying it to a finite number of points. That is considered to be the weakest case of discontinuity. So here we have an example, two functions, function f and function g, given on the picture. Function f is continuous at a, and function g is not continuous. The reason it is not continuous is that limit of the function g as x approaches a is not equal to the value of the function g, which is right over here at point a. G is discontinuous, but you can make it continuous by changing a definition. If we say that function g hat is defined as the following: when x is not equal a, we will continue to evaluate it using the expression for function g. But when x is equal to a, we will set it equal to the limit of function g of x as x is approaching a. For the new function g hat, the empty circle will be filled in. So the new function will coincide with function g of x everywhere except the place where there was empty circle. For g hat, the empty circle will now be filled in, and function g hat will be continuous. In general, we will say that function has a removable discontinuity if it coincides with a continuous function everywhere except one point. If there is a function that is continuous and it is equal to our discontinuous function everywhere except one point, we have a removable discontinuity. And functions with a removable discontinuity can be made continuous by modifying their description just at a single point. Let us take a look at an example. We need to show that the following function, sine x over x, has a removable discontinuity at x equals 0. Well, first of all, is this function continuous at x equals 0? The answer is no, because the function is undefined. Now the question is, what about all of the rest points? For all of the other points, the function is continuous. This can be verified by taking a limit as x is approaching some other value a is not 0, of sine x over x. As long as a is not equal to 0, that limit is evaluated by substitution. And we will have sine of a divided by a as long as a is not equal to 0. And we can see that for all other points, the function is continuous. So there's one single point where the function is discontinuous. And the question is, can be made continuous if we redefine the function. If we say define function f of x in such a way that for x not equal to 0, its definition is the same, sine x divided by x. But for x equals 0, we would like to use some other number. Can we pick that number so that the new function is continuous? Now, to pick that number, we need to satisfy the following properties. Value of the limit of the new function as x approaches 0 should be equal to the value of the function at 0. If this property is true, then f hat will be continuous. I'm skipping the property A where the function is defined. That property is trivial because we do define that function. And I'm skipping the second property where the limit has to exist. We're going to work on it momentarily. But assuming the first two properties are true, the third property says that limit should be the same as the value, and that will determine that question mark. In fact, it says that this question mark should be equal to the limit of the function f of x, f hat of x, as x is approaching 0. Okay, so let us take a look at the limit of function f hat of x as x is approaching 0. When we're talking about limit as x is approaching 0, we can exclude 0 itself from consideration. And if x is not equal to 0, we know which expression we need to substitute for the f hat. When x is not equal to 0, we should be using sine x over x instead of f hat. Very good. That limit is a special trigonometric limit. We considered it in the previous segment, and that limit is equal to 1. It exists. Therefore, the property 2 is satisfied, and the only thing that we need is to satisfy the third property, that the limit is equal to the value of the function. But our consideration suggests to set that value equal to the limit, which is precisely 1. So if we put that value for x equals 0 and change the definition of the function, so now it is defined at 0 and gives value 1 at 0, the new function is continuous everywhere. The original function was continuous everywhere except 0. And the new function coincides with the previous function everywhere except for 1 point. And it is built so that it is also continuous at that 1 point x equals 0. Since we were able to make the function continuous by modifying it just at single point, we can say that function sine x over x has a removable discontinuity at x equals 0. Going from less severe to more severe violation of the condition of continuity, we will introduce discontinuities of the type finite jump and infinite jump. Their names speak for themselves. A finite jump discontinuity corresponds to the cases when limits of the function exist from left and right. However, left limit and right limit are not the same. As a result, a function jumps from one value onto another as we cross a particular point. Because that jump is finite, we say the function has a finite jump discontinuity. Now, example on the right shows a function for which we have an infinite jump discontinuity. In that case, at least one of the limits, right-sided limit or left-sided limit, at least one of them or both will be infinite. In this case, as we go from left to right over a point of discontinuity, the function will have to experience an infinite jump in the value. Discontinuous functions arise naturally in life sciences. If we're looking at the population dynamics of, say, fish in the lake or large animals, mammals in the forest, we expect that the number of population will be given in integers. At the same time, this number will change where a death or a birth occurs, which is an event that will move the population from one integer onto another. As a result, we expect to see a discontinuous function. Here we have a couple examples that come from life sciences. On the left, I have a graph of the population of a bacterial colony. And if I start with just one bacteria, it will divide after a period of time, making 2, then 4, then 8, then 16. And the period of time will be shown on the horizontal axis, and the resulting population is on the y-axis. And as you can see, the population will develop in a discontinuous fashion. Another example we considered in the previous segment. Here we have a model for population that accounts for catastrophic collapse when the quality of the neighborhood degrades below a threshold level. There is an extinction happening in the population, and that model is also corresponds to a discontinuous function, as shown on this graph. Just because the true biological process is discontinuous, it doesn't mean that it cannot be modeled by a continuous function. Continuous functions are easier to handle mathematically. In particular, you have the whole calculus machinery that works for continuous functions, and it is more suitable for implementing it for computation. Now, what usually happens is that we start with a process that is discontinuous in nature, but we approximate it with a continuous model. For growth of bacterial colony, we can consider the situation where we can neglect what's happening in a short time. Suppose we're looking for a very long time period, or the bacteria reproduces in a very short time period. And then, of course, there will probably start with a larger population, so not all of the bacteria will divide at the same time. Some are already in the process of division, some are just divided, and they're growing at the moment. So as a result, we do expect that at the time scale that we're interested, we can approximate the discontinuous process, the true discontinuous process, with a continuous curve. However, we have to be mindful whether our modeling with continuous curve still applies to the problem that we're trying to study. Let us discuss a couple additional properties of continuous functions. One interesting property is the relationship between the continuity and the limit. In particular, that applies to the way we can evaluate limits. In the previous segment, we talked about the direct substitution property, which is a theorem that you can prove rigorously. Usually I prove it as a set of results for different kinds of functions. And the conclusion of that theorem is that if we have a polynomial, rational, trigonometric, logarithmic, or exponential function, and if number a is in the domain of that function, then limit can be evaluated by substitution. Hence the name direct substitution property. But if we look at that result in the theorem, we realize that this is nothing but the definition of continuity. As a matter of fact, what this theorem is stating that all of these functions are continuous. We will restate this result as a statement about continuity of elementary functions, in particular power function, polynomial, rational function, trigonometric function, logarithmic, and exponential functions are all continuous for all points in their domain. What can we do with continuous functions? We can add them, subtract them, multiply them by another, and divide. We can take roots and we can raise into powers. It turns out that if you start with two continuous functions and you perform algebraic operation on them, you get another continuous function. The situations that require special attention is division. We don't want the denominator to turn into 0, but as long as that doesn't happen, fraction of continuous function is a continuous function as long as denominator doesn't turn into 0. And we can also evaluate radicals. So radical of a continuous function is a continuous function as long as the radical is defined on the corresponding values of the function. Another operation that we didn't discuss is a composition, when one function can be used inside another function. Here's a couple of theorems that address that. The composite limit theorem says that if function f is continuous at point x equals L, and if we have function g that has a limit at some point, and the value of limit is L, that very same L is here, then we can evaluate the limit of a composite function, the composition of function f and g, which is defined as f applied on g of x. If function f is continuous, then the limit can be evaluated by bringing it inside of the argument. Limit of the composition is value of the function f evaluated on the limit of function g. And that limit is equal to L, so we can write it as f of L. But the short way to think of a statement that limit can be dragged inside a continuous function. Now, this theorem can be generalized a little bit further, and we can add the condition that function g itself is continuous. In that case, the limit of the function g as x approaches a should be equal to value of the function of g at point a, and we can rewrite that statement slightly differently. Again, we'll look at the composition of the two functions, and we use the result above, knowing that the limit can be dragged inside the function's argument. Now, we do know, because g is continuous, that limit can be replaced with the value of the function g of a, and we notice that f of g of a, it's simply value of the composite function evaluated at point a. If we compare now left and right parts of this equation, we notice that we're looking at the definition of continuity applied to the composition. As a result, we can formulate the following statement. If we have function g that is continuous at point A, and if we have function f that is continuous at point L equals g of a, then the composition of the two functions is also continuous at A. The short way to remember this theorem is that the composition of continuous functions is continuous. Let us now consider how properties of continuous functions can be used to solve examples. In this example, we are given a function given by this expression, and the question is, for what values of the variable is the function continuous? So we're trying to see what is the largest set of points on which the function is continuous. Well, we notice that inside the function we have the expression x squared minus x plus 3. That is a polynomial which is continuous everywhere. A polynomial can be evaluated at any point, and at any point the limit of a polynomial is computed by substitution. Therefore, polynomial is continuous at all points. That polynomial appears inside a function sine x. Sine x is also continuous at all points. By the theorem that we discussed, a composition of two continuous functions is continuous. As a result, we conclude that this new composition, the sine of x squared minus x plus 3, is continuous at all points. Now, to get to the original function, we need to do one more operation. We notice that it's a sine cube, so we need to take that result and cube it. So cubing is a special case of a composition of a polynomial and a sign. So this is a composition of a polynomial. Well, we can also think about it as a power function, because polynomial usually consists of several terms, but this particular polynomial has only one term, so it's a monomial, and the coefficient is 1. Well, in fact, it's just a power function. Nevertheless, we can think of it as a composition of a polynomial and a continuous function. Specifically, this one, that continuous function. And by the theorem that we just discussed, since both functions are continuous everywhere, and both functions are defined on the entire Euler number line, we conclude that this composition is continuous everywhere. So, as you can imagine, that's a very repetitive argument. You can see that the big function, the sine cube of x squared minus x plus 3, is broken into two consecutive compositions with various functions, and at each step of the way the functions are continuous. So the argument is that a composition of a continuous functions is continuous, and then another composition of continuous functions is continuous. It's a pretty repetitive argument, but we convince ourselves that in this case the result is a function that is continuous for every point x on the real number line. Let us consider one extra example. For what values of x the following function is continuous? If we look at the function, we see a ratio, a fraction. And when we talk about continuity of a fraction, we worry about two things. Both numerator and denominator we would like to be continuous. And we would be asking a question, when do both numerator and denominator are continuous? And second thing that we're worried about is that denominator is not 0. So let us try to think about these two conditions. The numerator, x to the 5 minus x plus 4, is a polynomial. It is continuous everywhere. Okay, now what about the denominator? So the denominator is square root of the quantity 4 minus x squared. And there are two things we are worried about. First of all, we want it to be not equal to 0, which in turn requires that 4 minus x squared shouldn't be equal to 0. And the second is that we want it to be a continuous function. Now, we do know that the square root of x is continuous for values of x greater than or equal to 0. So then we have the condition that guarantees that the square root of 4 minus x squared is continuous is 4 minus x squared is greater than or equal to 0. Now, combining with that first condition, that the whole denominator is not equal to 0, we notice that the equal to 0 part would disappear. So there are different ways to go about it. One way is just to solve two conditions separately, and then combine the results towards the end. 4 minus x squared not equal to 0 results into the condition that x cannot be 2 or negative 2. And the second inequality we can consider separately. There are different ways to go about it. One way is to factor and do sign analysis. Another way is to notice that, well, maybe we should do factors. So here we go. We can factor this expression 4 minus x squared as 2 minus x times 2 plus x. And that will tell us that we're looking at a parabola with the roots at minus 2 and positive 2. And that parabola opens down. And that is the graph of that expression. Y equals 2 minus x, 2 plus x. From Here we conclude that the value of the entire expression is negative if x is less than -2 or if x is greater than 2. Now, it is greater than or equal to 0 if x is between 2 on the right and -2 on the left. If x is between two values, we know that 4 minus x squared is guaranteed to be greater than or equal to 0. We get that from the picture. Alternatively, we can do sign analysis. We can take a look at what happens to these multipliers. I'm now giving you an alternative solution, so you may or may not do it like that on the test. It's a good way to do it, so let's take a look. Say example, for the first term, I know that first term turns into 0 at 2. And if we go to the left of 0, we'll be subtracting less, so I expect a positive sign on the result. And if I go to the right, I'll be subtracting more, so I expect negative result. The second term at 0 at -2, and if we go below -2, the total will be negative. But if we go above, the total will be positive. When we combine the signs, we realize that the total expression, the 4 minus x squared, will be positive between -2 and +2, and it will be negative after 2 and before -2, which is the same result as we got here on the right. We now will combine the two results. The first condition says that x cannot be equal to 2 or -2. The second condition, x should be greater than or equal -2 and less than or equal to. Combining these two results, we conclude that square root of 4 minus x squared is strictly greater than 0. That's what we need for the denominator to not to turn into 0 if x is strictly between 2 and -2. Okay, if this condition is satisfied, then square root of 4 minus x squared is continuous. And greater than 0. In that case, division by it will not result in losing continuity, and both functions are continuous, so the entire fraction will be continuous. The fraction f of x equals x to the 5th minus x plus 4 divided by square root of 4 minus x squared. We will consider one additional result about continuous functions, known as the intermediate value theorem. The intermediate value theorem is an important theorem in calculus. It's a technical result, but it supports a lot of other theorems. Now, in this particular course, intermediate value theorem is used to prove that equations have solutions, that you can solve them. Now, what does the intermediate value theorem is about? Well, let's formulate it. Suppose we have a function on the interval ab, and suppose w is a number between f of a and f of b. So we evaluate function at the endpoints, evaluate at a, evaluate at b, and w is a number that's between these two values. If the function is continuous on the interval, then we can guarantee that a number c can be found on the interval such that value of the function at c is precisely w. All right, so let's unpack that theorem. So first of all, let's look at the plots on the right here. And we have a continuous function f. We can see that f of x is continuous. It is defined on an interval from a to b. And values of the function at the endpoints, in particular a is -2 and b is +2. Values are given and they are right here on the axis. F of b seems to be 3, f of a seems to be 2.4, -2.4. Very well. W is a number between f of a and f of b. Because values of the function go on the y-axis, w also goes on the y-axis. And here comes it's between f of a and f of b. Very well. What's happening is that function will take on different values. And we know that at the left endpoint it takes of value f of a, and at the right endpoint it takes on value f of b. The claim is that the function will take on every value in between f of a and f of b. So if we pick a value w and we put a horizontal line like so, because w is between these two values, function will take on it. And that means that it will be equal precisely w at least one point on the interval. We cannot tell what point, but we do know that the point is there. Let's take a look at this illustration on the right. It's the same function, the same interval. What is different is a different choice of w. Well, w is still between f of a and f of b, therefore the theorem can be applied. And according to that theorem, there will be at least one value of c such that f of c is equal precisely w. But if we look at this illustration, we will see that we don't just get 1 point. We actually get 3 points. 3 points, and if we evaluate function at every point here, like this C1 and C2, and the original point C, f of C1 equals f of C equals f of C2, and all of them will return the same value W. Does that contradict the theorem? No, it doesn't. The theorem says there is at least one such number. Now, the fact that we found 3 does not contradict it. Probably the easiest way to remember the statement of intermediate value theorem is following. The intermediate value theorem says that the continuous function will take on every value between f of a and f of b. It will not skip a single value in that range. At some point on the interval, the function will take on that value. In this course, the intermediate value theorem is commonly used to prove that equations have solutions on specified intervals. Let us take a look at this problem. We have equation x squared plus 3x minus 2 equals 0. And we need to show that this equation has at least one solution on the interval between 0 and 1. Now, how can the intermediate value theorem be applied to answer that question? Well, we need to take a look. So, intermediate value theorem says that if f of x is continuous on the interval from a to b, then f takes on every value between f of a and f of b. Now, how this can be used to solve equations? Well, if we have equation, say f of x equals 0, then we can check whether f of a and f of b have opposite signs. Say one is positive, one is negative. Well, if they do, then w, that is equal to 0, will be in between. It will be in between. They are opposite signs. One is positive, one is negative. 0 will be in between. we can use that W and use the intermediate value theorem. And intermediate value theorem states that f of x must take on W equals 0, which means that there is a point C such that f of C equals W equals 0. But that C is a solution to equation f of x equals 0. That's the whole plan, right? So let's see how this plan can be applied to this particular equation. The equation we have at hand is x squared plus 3x minus 2 equals 0. The idea would be to take that equation and write it as f of x equals 0 for some function f of x. Clearly, if we pick f of x equals x squared plus 3x minus 2, then the equation that's given to us will be precisely in this form. The next thing to check is the value of the function takes on opposite sides at the endpoints. In our case, a would be 0 and b would be 1, the left and right endpoints. So let's evaluate. When we substitute 0 inside the function, we'll get 0 squared plus 3 times 0 minus 2, altogether minus 2. And then we will take f of b. B is equal to 1, so we have f of 1 squared plus 3 times 1 minus 2. That's going to be 1 plus 3 minus 2, which is 4 minus 2 equals 2. Well, the first value is negative and the second is positive. So indeed, the function is taking on values of opposite side. Then, by the intermediate value theorem, there is a C that belongs to the interval from 0 to 1, such that f of C equals 0. Let me add a tiny illustration to this problem. So we have a interval from 0 to 1 on the x-axis, and we just discovered that at 0 the function starts at -2, and at 1 the function is equal to 2. And we do know that the function is continuous, so it'll have to go from here and it will have to arrive over here. And because the function is continuous, it cannot skip on a single value. Therefore, the function will have to cross the x-axis. And that point will be the point that we're looking for, because at that place, the value of the function is 0, and that is the solution to the equation. Let us consider one more example of using intermediate value theorem to show that equations have solutions on specified intervals. Just to recap, the approach is to look at the equation in the form f of x equals 0 and check if the function is continuous on an interval, and also check if the values of the function at the endpoints f of a and f of b have opposite sign. If they do, then we must be looking at the following situation. So we have an interval from a to b, and f of a will start on one side of the x-axis, but it will have to end up on the other side of the x-axis. And if the function is continuous, that means that it will have to cross the x-axis. And that crossing point is that what we're looking for. At that point, value of the function is 0. So if the function is continuous and values of the function at the endpoints have opposite signs, then by the intermediate value theorem, there exists at least one point on the interval from a to b such that value of the function at that point is 0. So let's look at our problem. The equation that we are given is 2 cosine x equals x. And that equation is not in the form of f of x equals 0. But it's not very difficult to bring it into this form. So if we have 2 cosine x equals x, we can subtract x on both sides, and we will have 2 cosine x minus x equals 0. Now, if we define f of x to be 2 cosine x minus x, then our equation is in the form that we could be using. Very well. Let's look at the function. 2 cosine x minus x. Cosine is a continuous function everywhere. X is a continuous function everywhere. So we conclude that f of x is a combination of two continuous functions and is a continuous function on the entire real number line, and in particular on the interval in question. And the interval in question is from 0 to pi. Very well. So the first condition of the intermediate value theorem is met. Now let's check the other condition. What about the values of that function at the endpoints? A is equal to 0 in our case. B is equal to pi. So f of a, which is f of 0, is 2 cosine of 0 minus 0, which is 2 cosine of 0, which is 2, because cosine of 0 is 1. Now, f of pi, on the other hand, is 2 cosine of pi minus pi. And let's take a look. So the graph of cosine is going to be something like that, where pi is over here. That value is negative 1. That value is positive 1. So what we will have 2 minus pi. Now pi is approximately 3.14, so when we subtract pi, the answer is strictly negative. And the first value, f of 0, was equal to 2, which is strictly positive. So in that case, I see that my function will have to start above the x-axis, over here, and it will have to end below the x-axis, over here. By the intermediate value theorem, the function will have to take on every value between f of a and f of b, including value 0. Therefore, by the intermediate value theorem, there exists a point C on the interval from 0 to pi such that f of c is equal to 0. In conclusion, let us consider a couple of additional examples of working with continuous functions. So the problems that we will look through, they are very typical for exams, and it's worthy to study. So here we go. The first problem says find a value c that makes the function continuous everywhere. And the word everywhere has to be addressed, but that's usually not the core of that problem. So what do we see in that function? It's a piecewise defined function, and for all values but x equals negative 2, this function is defined as sine of x. For all values of x except x equals negative 2, f of x is equal to sine x. And sine x is a continuous function. It's a function that is continuous everywhere. Therefore, from the get-go, we know that this function is continuous everywhere except possibly x equals negative 2. The only point that is in question is the point x equals -2 itself. So we only need to check if f of x is continuous at x equals -2. Very well. How do we check the continuity? Again, three properties. F of -2 is defined. Limit as x approaches -2 of f of x exists. And limit as x approaches -2 of the f of x is equal to the value of f at -2. Well, let's see. The first property is true. We know when x is equal to -2, f of -2 is precisely equal to that constant c. If we look at the limit as x is approaching -2, we know that when we talk about limits, we don't have to consider x equals -2 itself, so we can focus on points x not equals -2. And for all of those points, the function coincides with the sine x. And the limit of sine x can be computed by substitution. So it's going to be sine -2. So that takes care of the first and second property. They all checked off. The only thing that's left, we need to make sure that the limit that we get over here is equal to the value of the function that we get over here, which means that sine of -2 should be the same as that constant c. If the constant c is like that, then the function meets the third property and the function is continuous. Thus, we set c equals sine of -2. That will make the function continuous. Let's take a look at the following problem. A certain sample is kept at the temperature 4 degrees Celsius. To conduct an experiment, the temperature of the sample needs to be raised to 21 degrees Celsius. It turns out that sample can be sensitive to a rapid temperature change. And in that case, we would like to raise the temperature gradually, and therefore sample will have a chance to adapt and have at the same temperature across the sample. For that, we can use a special chamber that gradually raises the temperature. Now, the temperature-controlled chamber can be programmed to raise the temperature according to the following linear function, where T is in hours and temperature is in degrees Celsius. So we need to find the values of coefficients A and B that would allow the chamber to warm up the sample over the period of 5 hours without jeopardizing its integrity. Okay, so what do we know about this problem? So first of all, let me think about the time in hours. And at the beginning, the sample has a temperature of 4 degrees. At the time 0, the program will kick in and the temperature will start to gradually rise according to the linear function. And by the 5 hours, after 5 hours, so that'll be 1, 2, 3, 4, 5. After 5 hours, the temperature is desired to be 21. And most importantly, we would like to make sure that there is no sudden jumps in temperature. So we would like to start to raise the temperature according to a linear function. And it would have to start exactly at 4 degrees and would have to end exactly at 21 degrees. So let's see, what does this tell me about my function? So in particular, I know that the function t, given by this formula, we know that value of the function at the point 0 should match the value of the temperature that was before the point 0. So we can express it in the following limit statement. So when t goes to 0 from the right of t of t, that would be approaching that 0 from here, the value of that would be meeting the value of the temperature before 0, which is precisely 4 degrees. At the same time, when we approach value of 5 from the left, which would be that value over here, then we would like to see 21. Now, evaluating the limit as t goes to 0 plus of t of t, that's the same as to say temperature goes to 0 plus of at plus b of that linear function. And because that's just a polynomial of first degree, we can evaluate that limit by substitution. That would be a times 0 plus b. That's which simplifies into b. And we know that that limit have to be equal to 4. So we conclude that b is equal to 4. Very well. Now let us go to the second condition that we derived. Instead of the formula for the function t, we will have to write at plus 4. You see, I already substitute 4 instead of b. And that limit as well can be evaluated by substitution. So it will be a times 5 plus 4. And that is the value of the limit. So we have 5a plus 4 on one side and 21 on the other side. We can solve for a. So in particular, 5a equals 21 minus 4. So that means 5a equals 17. So a equals 17 over 5. Here we go. That's the value of a. If we choose these values, then our linear function, that's 17 over 5t plus 4, will meet the corresponding ends, and the temperature raise will be continuous. Let us consider one more example of a problem where we need to choose a parameter to make the function continuous. In this problem, we are given a piecewise defined function, and the expressions in the function, they depend on the parameter, d in this case. And the claim is that for a particular value of the parameter, this function can be made continuous. One of the things that we can notice that regardless of the parameter d, which is a constant, for x strictly less than or equal to 3, the function is a polynomial. Well, maybe I should write that x strictly less than 3. So for all of the points that come before 3, function is a polynomial. And polynomials are continuous everywhere. So as far as this function is concerned, even as is for any value of the parameter d, this function is continuous already for x strictly less than 3. Absolutely the same way, we notice that for x strictly greater than 3, the function is also a polynomial, and therefore it's already continuous regardless of the value of the parameter 3. And it is also continuous for values of x strictly greater than 3 regardless of the value of the parameter d. So d doesn't matter for the continuity of the function for x less than 3 and for the continuity of that function for x greater than 3. So we only need to consider continuity of f of x at x equals 3. So what are the conditions? Well, the function has to be defined, and the function's limit must exist as x approaches 3. And finally, limit as x approaches 3 of the function f of x has to be equal to the value of the function at 3. So there's 3 conditions. If these 3 conditions are satisfied, then the function is continuous. Well, as far as being defined, the function is defined at 3. We would have to use the top formula. F of 3 is equal to 3 squared plus d times 3 minus 1. Altogether, after simplification, we have 8 plus 3d. Very well. That value depends on the parameter, so we just put it here and we will see how to use it later. When we look at the second condition states that the limit of function f of x exists as x approaches 3. And here's a catch. When we look at the function, we actually have 2 relevant formulas. One we use when x is less than 3, and another one we use when x is greater than 3. So when discussing the limit at 3, we would have to use different formulas depending on which side of 3 we are. Well, that's not a big deal because we can use one-sided limits. So in particular, limit as x approaching 3 from the left of f of x, for that limit, we would have to use the first expression over here. So we will write x squared plus dx minus 1, and we evaluate that limit by substitution. So it would be exactly the same value as we just computed, so I'm writing here 8 plus 3d. Now, if we look at limit as x approaches 3 from the right, now we need to have the second expression here. So limit as x approaches 3 from the right, instead of function we substitute x plus d. We evaluate that limit also by substitution, arriving at 3 plus d. Now, for limit in general to exist as x approaches 3, we must have left and right limit to be equal to each other. Therefore, we need to have 8 plus 3d to be equal to 3 plus d. Well, that is in fact an equation that determines what the value of d should be. We can solve that equation over here. Let me see. 8 plus 3d equals 3 plus d. We can simplify. We can move everything that has d into the left side, and everything that has doesn't have d we will move to the right side. So we'll have negative 5. And finally, d is equal to negative 5 over 2. So here we go. That value of d will make sure that the limit exists. This value implies that that limit exists because left limit will be equal to right limit. That means that limit in general will exist. So it turns out to satisfy the second property, we already need to select a particular value of d. So what about the other properties? Well, the first property we don't particularly need to worry about because all it says that when you have value for f of 3, which is 8 plus 3d, we now need to plug a specific value, 5 over 2. So negative 5 over 2. So we will have 8 plus 3 multiplied by negative 5 over 2, which simplifies to 8 minus 15 over 2, which is 1/2. The last property to check is the third property, which says that the limit as x approaches 3 is equal to the value of function f at point 3. And that property is automatically satisfied. In particular, when we were looking at existence of the limit, we set limit on the left and limit on the right together. So look at this. So this was the limit as x approaches 3 from the left, and this was the limit as x approaches 3 from the right. And both of these values are the same. So we computed d so that these values are the same. So if we substitute d equals -5/2 on both sides, on the left side we'll have 1/2, and on the right hand side we will have 1/2. It's not a surprise. It is how d was computed. But what is 1/2? 1/2 is the value of the function at 3 on one side. On the other side, that's the value of the limit. That limit is equal to 1/2. And these values are the same, so property 3 is automatically satisfied.